In the previous video, we learned what the definition of an isomer was, that being a compound that has the same chemical formula as a given alkane, but where the atoms of that formula are arranged in a different bond structure, resulting in different molecules. And in this video, we're going to learn that not only are these compounds all distinct compounds because of their structures, but that every single one of them requires a unique name to signify that these are, in fact, different compounds. So we're actually going to leave all of these isomers of the simplest form of the molecule, that being hexane, and we're going to take a look down here, going over a step-by-step strategy in order to name and draw these structures of much more challenging examples of alkanes. So the very first thing that you need to do when looking at a relatively overwhelming molecule is to find what we call the longest carbon-to-carbon chain, which is also what we call the parent chain of the molecule. So if we were to do that, we can actually look, and if we see 1, 2, 3, 4, 5, if we try in any other way, we get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So one way or another, the parent chain of this molecule contains 5 carbons, which we can represent with the prefix pent. Since there are only single carbon-to-carbon bonds within this molecule here, we can identify that the parent chain is indeed pentane. Now the question is, well, what do we do with the rest of the molecule? Well, any carbon or carbons, in this case here, that are not distinctly part of the parent chain but come off of the sides of the parent chain are exactly what you would expect chains coming off of the side to be called, that being side chains, although they are more correctly known by the term alkyl branches. And alkyl tells us a little bit of a hint about how these side chains are named. Now, before we jump into how the naming system would work, we should identify what kind of alkyl branch all of the side chains are, and we do that the same way that we name the parent chain by counting the number of carbons that exist and referring to their prefix. For example, this side chain here only has 1 carbon, so we would use the prefix meth, meaning 1 carbon. This is another meth, and this is another meth down here, but we can see that this side chain actually has 2 carbons, and therefore this would be an F. Now, because these are not alkanes, because these are not complete molecules, but instead are side alkyl branches, we add the suffix -il or YL. So instead of methane, this would be called a methyl branch, or rather all of these single carbon side chains would be called methyl branches, whereas this 2 carbon side chain would be called an ethyl branch. Next, we need to designate each of these with a numerical prefix to indicate how many of each of these side chains exist within the molecule. Now, what we're going to do is set up the skeleton for how this name is going to work, and we are actually going to write ethyl on here first rather than methyl, because E comes earlier in the alphabet than M, and where all the side chains appear in the name is based on alphabetical order, which is why ethyl comes first. Now, we can see that there is not a single methyl. We actually have 1, 2, 3 methyls in this hydrocarbon compound, and we know the numerical prefix that indicates 3 of something is the numerical prefix tri. So this tells us that we have a 5 carbon long parent chain with only single bonds that contains a 2 carbon long side chain and 3 single carbon side chains in different locations. Next, we need to identify what the carbon locations are for each of the side chains, and in doing so, we need to identify what carbon number 1 is of the molecule. And I actually did that here, even if you weren't aware of what was happening here. So carbon number 1 always has to be a carbon on the end, whether it be the right or the left or the top or the bottom end of a molecule, because we can't start numbering carbons in the middle of the molecule. That doesn't make sense sequentially. But why did I choose to put carbon number 1 on the left-hand side of the molecule? Why didn't I put it on the right-hand side of the molecule? Well, the answer to that actually comes after we have named this molecule here. Now that we've identified where carbon 1 is and the numbers of all of the carbons in the parent chain, we can now identify the locations of each of our side chains. For example, this ethyl occurs on carbon 3, so we would indicate that with 3-ethyl, indicating 2-carbon side chain on carbon number 3. And because there are 3 methyls, we need to specify 3 different locations. This first methyl is located on carbon 2. We have a second methyl located on carbon 2, and a third methyl located on carbon 4. So the name of this monstrosity is what we would call 3-ethyl 2,2,4 trimethyl pentane. Rather cumbersome name, but remember that every component of this indicates some aspect of the structure that is important in determining what this molecule looks like. So, on to the question, why did we choose for carbon number 1 to be here? Well, carbon number 1 is always the carbon that gives all alkyl branches the lowest possible number when all of the numbers of locations are added up together. So for example, 3 plus 2 is 5, plus 2 is 7, plus 4 is 11 is the total number of locations. But if we did this the other way, 1, 2, 3, 4, 5, the total would be, we have a 2 on this methyl, a 3 on this ethyl, and 2 4s here. So 4 plus 4 is 8, plus 3 is 11, plus 2 is 13. So if we were to put carbon 1 on the left-hand side, the total location number is lower than if we were to put carbon 1 on the other side, and that's how we determine that carbon 1 is here. Now, most students find that drawing a structure from a name is significantly easier than going the other way, and for the most part, I would agree with that. We start with the parent chain, hexane, which tells us that there are 6 carbons, and these carbons are only single bonded, so let's go ahead and write that parent chain here. If we start with our first side chain, we have a ethyl, or rather we have 2 ethyls on carbon 3, and on carbon 4. Eth means 2, and il means that this is a side chain, so we have 1, 2 here, 1, 2 here. That's our ethyl taken care of. And then tetramethyl implies that we have 4 1-carbon long side chains, 2 on carbon 2, which would be here, 1, 2, 1 on carbon 3, and 1 on carbon 4, and that's the structure done. Now that you've had practice with both naming an alkane, a complicated alkane with side chains, using this example here, and drawing the structure of a complicated alkane from a given name, firstly, you can name all of the isomers of cyclohexane up below before moving on to these ultra-challenging molecules that you find on the next page.